The first speaker is Marian Rusnak. He's a senior software engineer and tech lead for the JavaScript ad client team at Yahoo. His team develops the SDKs for keeping the web available for free by loading all our beloved ads that we love so much. Marian has spoken at local JavaScript meetups in London, lectured at the University of Westminster, and the majority of his speaking effort has been related to promoting the tech industry among women by organizing web development courses and motivational workshops for a Women in Tech initiative. His talk will be something that I find super crucial. It is all the things that go into having a service that needs to handle many, many requests while keeping it reliable. So without further ado, let's get on with the talk.
Hi, my name is Marian Rusnak and I'm senior software engineer, and I'm happy to speak at Node.js Global Summit about how my team at Yahoo got into billions. And I mean billions of requests a day. How we designed and developed a web service which can handle such a load. Here is the agenda for today. It's good to start with a short intro. After that, I'll talk about the legacy systems we had to work with. Then about the development of a new system, its architecture, various tweaks and optimizations that were needed to handle large amounts of traffic. And finally, I'll tell you a few words about the process of migrating from the legacy systems to the new one. So let's start with the short intro. Some of you may be wondering, Yahoo, is that still around? It definitely is. It is still one of the top 10 most visited websites in the world. And just like many internet brands out there, its main income comes from, tada, advertising. And that's what the project I work on is about. But don't worry, today's talk is going to be mainly about the challenges we face when serving ads, and maybe you will actually like them. The challenges, I mean, not the ads. Let me also briefly introduce the team that made this talk possible. Our team at Yahoo is responsible for maintaining ad clients for different use cases, like display ads, aka banners, video ads, native ads, header bidding. Unfortunately, I don't have time to explain what each of these mean, but it is not going to be so important in the remainder of the talk. But because I'm going to use the term ad client a lot in the next few minutes, let me explain a bit more what it is. In a very simplistic terms, it is a tool or a library that lets a publisher fetch ads and display them to the users. So imagine you are a publisher like Yahoo, and you want to monetize your page through ads. What you do is you include some ad client library on the page, just like in the example on the right. And it gives you an easy way to fetch ads. You call fetch ad function and boom, you have ads where you want them. So ad client is something like an SDK for ads. Enough of introduction, finally onto the fun part, or maybe the sad part as it is about a legacy project. Anyway, I'll let you decide. Sometime back in 2018, our team inherited a couple of teenage projects. What I mean by teenage is that they were over 10 years old. And you might be guessing, right, what these projects were doing. They were ad clients. And there might be many great projects out there being over 10 years old, but this was a slightly different case for a few reasons. For example, the code was pretty messy, hard to read and understand, something like this. It looks more like some ASCII art than the source code, or some endless files, these being over 9,000 lines long. I said we inherited two projects and each had its own quirks. One was very complex and hard to maintain, as I've shown, and the other one was not achieving the security standards the company was aiming for. But most importantly, the functionality wasn't well covered with the tests, which left us with what I call a YOLO style development. Though we were never sure whether a change we do wouldn't break anything in production. And the code base inflated in those over 10 years, and even though a large portion of the code base wasn't needed anymore, it was impossible to simplify it. It was just nightmare to work with. So we decided to do what? Rewrite it from scratch. And I must say, rewriting from scratch is very rarely a good option. But when is a better time to do it? When you have a 10 plus years old projects and the team which developed or worked on them is no longer there. So let's talk about how we developed a new system. And what were we actually going to develop? Obviously an ad client. And from my previous example, we know it gives publishers API to fetch ads. But along with this new ad client, we decided to also create a layer between the ad server and the JS library. And this is what this talk is about. The previous legacy system also had such a web service in between, and we thought it might be a good idea. It serves as a backend for the JS library, and the payload can be controlled within a single team. And this speeds up development and migration from the old systems. The scope of this project was to use it across all web properties owned and operated by Yahoo. And this includes TechCrunch, Engadget, and also the mail web applications. But there is also a partnership between Yahoo and Microsoft, so that we provide ads on MSN and Outlook as well. And this scope created expectations for the system to handle over 2 billion requests a day. And the beauty or the challenging part of advertising, we couldn't afford any downtime, otherwise we would lose a lot of money. I cannot share exact revenue numbers, but I remember one incident when the service was down for less than an hour, and this resulted in hundreds of thousands of dollars in revenue loss. So we better made sure this happened only once. I'll share how we did it shortly. Another expectation was to deploy our service in AWS because the company heavily uses AWS. So great for those who are using AWS. Some things that I'll cover might be familiar. We knew the expectations of our service, so the next thing was to make a technology choice. We expected the app to be heavy in terms of network usage. This is because each incoming request results in at least one request to the ad server. And because we knew Node.js is good for non-blocking I/O operations, and because we had a good JavaScript knowledge in the team, we decided to pick Node.js, which is basically why I'm giving this talk at the Node.js focused conference. Another decision was to pick a framework to structure our application. We had past experience with Express, and we knew it was big in terms of popularity, but we wanted to check whether there aren't any other potentially better options. So we researched and found a few benchmarks which were suggesting Fastify, that it can achieve high throughput. I provided a link to the benchmarks created by Fastify maintainers. I don't think it's the one we found at the time, but as it was over 3 years ago, I just couldn't find it now. And maybe now you might have heard of Fastify, but back then it was a pretty new kid on the block. As our application was to be hosted in AWS, we had a few options how to host it there. We could spin up virtual machines. Those are called EC2 instances in AWS. And we could set up everything ourselves on those virtual machines. Or there's a service in AWS which lets you run Docker containers. It is called Elastic Container Service, or ECS. And it has two sub options to either run these containers on EC2 instances you control, or the instances that AWS itself controls, and that the latter is called Fargate. It is basically like serverless Docker containers. There is also an option to run it as Lambda functions, which we had used in other projects in the past, but Lambda is not suitable for large traffic due to its cold starts and high costs. I'll not have time to go like further details and pros and cons of each options, but we picked hosting the app using ECS on EC2. The main reasons for it were we wanted to use Docker containers so that we have similar setup locally as in production. So that's why we picked it over regular EC2 instances. And comparing EC2 on ECS on EC2 over to Fargate, it gives us more insights into the performance and allows us to fine-tune how many instances are running so that we use the resources optimally and have predictable costs. With Fargate, scaling is and costs are more like magic. Before going live to production with our application, we ran load tests. They were done in 3 stages, each having a different goal. Firstly, we wanted to uncover potential bottlenecks and issues like some process being done synchronously and therefore blocking the event loop. Then we needed to find the right instance type for our type of application, and finally find a sweet spot for auto scaling. I'll go into details in the next few slides. We spun up separate ECS Fargate task. It's this serverless Docker. The task ran a WRK testing tool to flood our app with traffic and shut down when finished. Here it was a good use of Fargate, as we didn't care about which instance it runs on and more about setup being simple. Very important thing to mention is that the results of our load tests were often affected by some variations in AWS. So because the app runs in virtual machine, which shares physical machines with many other projects. There are many virtual machines on the same physical machine, and there can be other projects on the same physical machine, and those other projects can have effect on the performance. So I can demonstrate this with this chart. It shows processing time measured by the app during multiple test runs. And the test runs I highlighted are using the same setup, the same level of traffic. It was really just a retry, and you can see the difference in processing time. So it was important to run load tests multiple times to verify, ideally in a similar time of the day, just to be sure. And I would like to stress that it's very important to set the right goal and observe the right metrics when running load tests. Otherwise, you can easily make some false conclusions. With our first goal to find the bottlenecks and issues inside the app, we ran tests with increasing traffic against a single instance. There was no need to spin up multiple instances, as this would just hide potential issues. And after the test, we looked at metrics like CPU, usage, memory, and network, checked whether they are increasing, checked for errors and crashes. We tried to spot whether there is something blocking the app from handling more and more requests. After we found some issues and fixed them, we moved on to the stage 2, where we tried finding the right EC2 instance type. There are tens of instances, if not hundreds, available in different sizes, so it might not be trivial to choose the right one to maximize performance. We started with RPS with acceptable performance from the previous stage, tried different machine types and sizes, looked at metrics like CPU usage, memory, network, to see whether there is some room for more RPS, and if there is, we increased it, reran the load tests, and etc. And when comparing RPS between different instances or different sizes, we had to take into account costs as well. So if a machine can handle double the RPS because it has double the CPU cores, it can also cost twice more. So we needed to take this into account. We picked the best instance type. It was C5X large with 4 cores, if you are interested. And the last thing we wanted to get from the load test was the best thresholds for auto scaling in order to use resources optimally and save costs. Here we mainly looked at the points where metrics, mainly the processing time, got unacceptable. We set the auto-scaling thresholds just below that point when the performance and the processing time gets unacceptable. And then we verified with load test that auto-scaling works fine. Let me now show you a bit from the architecture. Let's start with a simple diagram. We built a Node.js app, by the way, it's called Geekle. It uses Fastify framework and receives requests from users' browsers on the left and makes requests to the ad server in order to fulfill these requests. This is displayed on the right. In fact, there are multiple of these ad servers, and even one request from a user can result in multiple ad server calls. It's good practice to put Node.js service behind a proxy. We picked Nginx for that. We let Node.js to deal with what is good at, which is handling these non-blocking network calls, and it doesn't have to do the CPU intensive stuff like SSL termination or gzipping. We offload that on Nginx. All of that is being done in a Docker container, so we can deploy it in AWS on ECS, as I said. Each ECS task is composed from multiple Docker containers. In addition to the app container, there are also Telegraph and FluentBit containers. These push logs and metrics about the app into a separate service. This is essential when running apps in the cloud, and especially with high traffic, because you cannot do things like send logs into a file, as the machine can go down at times. We push logs to Splunk, which is managed by another team at Yahoo, and we push metrics into an internal tool called Yamas. It's like a Datadog or New Relic. As I mentioned, we decided to run ECS on EC2. So each EC2 instance runs a single set of these Docker containers. And with high load, we automatically spin up more EC2 instances as needed, which is called auto-scaling, as I mentioned. And because we have multiple machines to handle the traffic, we need to put a load balancer in front so that users can hit one host name, and load balancer distributes the traffic evenly across all the machines. Hopefully this diagram kind of makes sense. Let me also touch on our development process. It is composed of three main pieces, which I'll explain in more detail in the next slides. But there's a Geekle repo with the source code, infra repo where all the infrastructure is defined as a code in the YAML files, and this is responsible for applying changes onto AWS. And then we have automated build that run weekly and refresh SSL certificates or update AMIs. It's like a virtual machine image in AWS. Here is a screenshot from our CI/CD tool called Screwdriver. It is also open source tool available on GitHub. And this screenshot is showing the pipeline for Geekle's repo, so the application where the source code is. And the pipeline is responsible for building and publishing Docker images to the Docker registry. So on each merge of a pull request to master, there is a release candidate version published automatically. And when we want to deploy to production, we publish a stable version using a single click. So that's the bottom part of the pipeline. Infra repo, it contains infrastructure as a code, which in AWS terms is called CloudFormation. And every time we want to change a version in production, we create a pull request and change a parameter file like the one you see on the right. So we just change the version parameter in the file, create pull request, and when it's merged, a new Docker image gets pulled in AWS. A very important feature we implemented is support for running canary versions for a small percentage of traffic. In the same parameter file, we can specify a version and a percentage, and when this gets merged and deployed, the load balancer would split the traffic based on this percentage. And so we ran, for example, 5% of the traffic with the new version and 95% of traffic with an old version. I should add this is supported only by application load balancer in AWS, not the network load balancer. And the deployment pipeline looks like this, which might seem kind of complex, but mostly it is because of support for canary versions and also having 5 regions in AWS. So each regional deployment, it consists of 3 different jobs. One is a preparation, the second one is the actual deployment, and then the last are smoke tests, which hit the application URL with a test payload. And here is the pipeline for the weekly builds, which run on Sundays and update AMI and SSL certificates. These updates are automatically applied to QA and stage environments, and a pull request is automatically created for the production environment. So when we come to work on Monday, the pull request waits for us, and we just check if everything looks okay and merge and deploy it. Here is Jill in a few numbers. Currently, it handles 1.17 billion requests a day with 52 machines across 5 AWS regions at peak times. For 99% of requests, it spends less than 3 milliseconds processing them, and it is well covered with tests. We have 480 end-to-end tests, which make real HTTP requests and validate the responses. I would like to share a few tweaks and optimizations we had to do in order for the app to handle such a high traffic. The very basics are using a long-term supported Node.js version and a slim version of the Docker image. The slim image does not contain dev tools like the regular Node.js image. Because Node.js is single-threaded, so in order to leverage multiple CPU cores and maximize performance, we use PM2 inside the Docker image, inside the Docker container. Our C5X large machines, they have 4 cores, so PM2 starts 4 Node.js processes. We also increase the limit on the size of HTTP headers to 65 kilobytes. This is done by setting this max HTTP header size CLI flag. It used to be 65 kilobytes in the past, then it was lowered in some version of Node.js. So basically we just set it to the previous default. In order to handle many concurrent connections, we increase the limit on the number of open files in Linux because network connections are represented as open files in Linux. And this limit is called ulimit, and we set it to 50,000. And also we increase size of threads that libuv uses. Libuv is a C++ implementation of Node.js event loop. And we set it to 16. I think the default is 4. So usually, no matter how much you prepare your app to be production ready, there will be some cases in production which surprise you, which you haven't accounted for. Like this one, when one third-party digital out-of-home partner integrated with our service. This digital out-of-home partner was running ads in real screens in shops, and their implementation created large spikes of traffic because they make all their requests from hundreds of shops at the same time. Don't ask me why. But this overloaded our machines and led to requests being dropped, especially at off-peak times because the number of running machines was small at the off-peak time. So in order to handle these large spikes and be able to buffer thousands of requests coming at the same time, we had to increase some kernel flags, which are shown on the slide. We also increased worker connections Nginx config option from 512 to 2500. And with these, we were able to handle the spikes, and 500 HTTP errors went away. Eventually, the DOOH partner also fixed their implementation and flattened the traffic, but we just made our app more resilient. We were able to reduce our costs in AWS to less than half, with the same, even increasing amount of traffic. And how we did it? We did two things. The biggest gain was sending logs to Splunk instead of CloudWatch, because more than a third of our cost prior to this was for CloudWatch. And second thing was removing NAT gateway. This makes our machines accessible from the outside world. They are public, but we secure them properly via security groups with some strict rules. Finally, let me mention a few words about the process of onboarding publisher websites and migrating them from the legacy system to this new one. So far, we migrated over 15 websites with over 60 regional combinations in total. This means there were many different code bases which had to be updated, and many development teams on each website had to be engaged. This is the timeline for the migration. Everything started back in 2018 when the team inherited the legacy projects. First thoughts of for the rewrite came in November that year, and December 2019, so a year later, we onboarded the first site. Later in May 2020, we onboarded a first high traffic site. So this tested the resilience of the new system. And November last year, we finished onboarding all sites which were using one of the two legacy systems which I mentioned. And we are still in the process of migrating off the remaining legacy system, which we hope to finish sometime next year, and then decommission the legacy system. What was crucial during the migration was having a consultant in a team who communicated with the publishers and he shielded the dev team. So if you're doing a multi-year migration effort, and I cannot recommend more getting a dedicated person for engaging with your clients. And what we realized along the way is that you can never log enough metrics. It is important to log as much metrics as you can. This will help you to uncover issues, and it is always good to confirm issues or resolve them with just by showing data. And with that, I would like to thank you for your time and looking forward to the Q&A.
That was an amazing talk, and I'm going to bring Marian onto the stage now. Hello, Marian. Maybe.
Hello.
Hello, Marian. How are you?
Yeah, good.
That was an amazing talk. Before we go on with the questions, I have a question of my own. What was the biggest struggle code-wise to implement at such a huge scale when moving from, because not only do you have to move from one system to another, you have to move from a legacy system to another system that has to handle a lot of throughput. So were there any kind of things that tripped you up, like memory leaks, like what kind of things took your team by surprise?
I don't think there were things like memory leaks and big issues in the app in terms of handling the request. But what was challenging was migrating many different code bases that publishers were using, and every code base was a project in itself. So every team that onboarded to our service was very cautious about not breaking any revenue when they migrated from the old system to the new one. So everything had to, like, all the numbers had to match, and so we had to. That's why I wanted to also say that metrics were very crucial, and we needed to make sure that we perform as good as the old system in terms of revenue and money and all that.
That sounds good. That sounds great. Great that you didn't have any trip ups. Let's move on to some of the questions. How long do your full 80 end-to-end tests run? A2 test run.
That's a good question. I know many teams are running tests for like hours, but yeah, they run pretty quickly in less than 10 seconds. In the CI/CD tool, which is called Screwdriver, as I mentioned, it's an open source tool.
Okay, that sounds great. How many pods do you have on your on one EC2 instance?
This is a great question. Yeah, I think I forgot to include this in the talk. We verified that the best performance is when we put only one Docker container in one EC2 instance. So speaking of pods, pods is used in the Kubernetes world. But in ECS, it's called task. So we only have one task on each EC2 instance. We compared how it was the difference if we put multiple tasks on one machine, but it didn't have better performance. So having one task on one EC2 instance gives us the best performance.
Okay. Nginx together with Node in one container, or does it mean that they're all separate containers?
Yeah, this is a standard question. Yeah, so I'm sure the Docker purists, they wouldn't like what we did, but we actually have Nginx and Node in one container. And again, we also verified this with load tests. It gives us better performance than having two separate containers for them. And also, at the time when we made a switch, we were also we wanted to also be ready for Fargate. I mentioned this in the talk a bit. We didn't go up with Fargate, but on Fargate, it would be easier to have one container. Okay, we didn't go with it at the end, but also having one container with Nginx and Node, it also gives us better performance. So that was the reason.
Okay. Let's see here. How does your load balancer handle the calls from the same customer so that it will be sent to the same pod even if the pod is overloaded? The point is maybe you have cache data of the customer.
Yeah, we don't need to deal with that. We don't have sessions, so all the requests that are coming in are independent, so we can handle it with any machine.
Okay. For the load test, what was your criteria to choose the use case or use cases to run?
Like we tried to cover all the majority use cases. So we wanted to cover the happy flows. So like just to mimic a valid usage of the app. And then also, on the other hand, we validated some error usage, whether we handle it gracefully.
Sounds great. What is the best load testing tool for Node.js?
So for basic load testing, like if you want to do it locally, we used AutoCannon. And for the actual load testing of a real application, everything spun up in AWS. As I explained, we spin up a separate task and run a WRK tool on that separate task. And that separate task will make 2,000 requests a second to our application. It will stop after 15 minutes, and then we check the metrics in Yamas or CloudWatch, how we performed, how the application performed.
Okay.
Yeah, we use WRK.
Okay.
We also, I think we tried using some other tool which is written in Go. I forgot the name, but yeah, I think WRK was okay for us.
What alternative you used instead of CloudWatch?
Oh yeah, we use Splunk. I think I
Yeah.
mentioned we
Yeah.
yeah, like we have a we are lucky because other team maintains our own internal Splunk cluster. But there might be some like cloud services out there. So the thing is, CloudWatch is pretty expensive. So that was the reason we wanted to switch. I'm
You'd
sure
have
there
to handle like a different scale if it were to be feasible, or
are. So I think just CloudWatch is very expensive for the amount of logs you put there. I'm sure there are cheaper alternatives for the same amount of logs. You can find
yeah.
cheaper options.
A quick question is, could you provide us with the presentation?
The slides, yeah, of course,
Yeah, of course. Okay.
I'm not sure how it works. Like you'll share the slides afterwards for all the talks, or
we can get back to you on that one. So we'll make sure.
Mm.
How did you do the load testing exactly? Could you provide us with some examples?
So basically, I mentioned that we have this infrastructure repo where we have all the infrastructure defined in the code, and we also have that other ECS Fargate task defined there, and there is a line which specifies the WRK command, which is to run on that ECS task. So when we want to run our load test, we specify what are the parameters for the test. So how many concurrent connections we want to run during the load test, what's the duration, etc. Usually we run something like 1,000 requests per second, and we run it for 15 minutes or 10 minutes. I can't remember. We we save the file, and our CI/CD tool deploys this to AWS. And then in AWS, this ECS task will spin up and will make connections to our application. We'll make requests to our application. And then after 15 minutes, this ECS task will shut down, and we will check the metrics in the usual tools like CloudWatch or Yamas.
I think we have a little less than a minute left, so maybe we can take a few of the small ones. Wouldn't LB replace Nginx in this context?
This is a good question. So we have a requirement, the internal company requirement, that we have to have everything that is in transit have to be SSL. So we also have to have communication between load balancers, so ALB, and the EC2 instances. They also have to be via SSL. So we have to do the SSL termination inside the machine. And we didn't want to do it in Node.js. It's better to do it in Nginx. So that's why we have Nginx.
Okay. And then I think we can take one last question because it has to do with scalability. And I think that's important to touch upon. So can you explain shortly how AWS Lambda isn't cost effective and scalable enough? I thought that was the main selling point.
So when you put 2 billion requests against Lambda, first it's definitely going to be more expensive than just like ECS and running EC2 instances. Also, if you want to respond quickly to that many requests, like you want to respond in 3 milliseconds and don't want to have high latency, Lambda isn't good because it might have some cold starts, like machines might be starting up behind the scenes and etc. And yeah, I think these are the main reasons.
I think that makes a lot of sense. Thank you, Marian. That was an amazing talk and a lot of good questions and a lot of good answers. I think it's hugely important to touch on like scalability, because not only does Node.js have to be really good when you're building products that have to serve a small number of users, but it also has to grow with you. So making sure that that goes well is crucial. So thank you so much for your talk, and thank you so much for being here to answer questions.
All right, it was a pleasure. Thank you.
Thank you.